Sometimes expressions may appear equivalent, but they may not be exactly. How can you tell for sure? Well, let's look at these two equations first of all. Okay, look at these two equations. In these two equations, we want to show that the two functions above are equivalent by factoring and simplifying y sub 2. So how am I going to go about factoring y sub 2? Can't really do anything to the numerator, right? What about the denominator? Well, guys, I'm not solving, I'm just factoring, right? If I factor, I'm looking for what these terms right here, since there's only two of them, what do they have in common? An x? If I factor out an x, what's left? X plus 2. Does the numerator and the denominator each have a common factor? What is it? An x, right? The only time we can simplify things from a numerator and denominator is if they have a common factor. There's an x and an x in the numerator and denominator. Not this x. This x is part of another number, right? This x is a multiplier. It's a factor of the denominator. So I can simplify those. What is x divided by x? Guys, what's anything divided by itself? Oh, Lord, have mercy. Anything divided by itself, for example, 2 divided by 2, or 5 divided by 5. Okay, so I'm going to start this part over again. You ready? So the numerator and denominator both have an x, so I can simplify that out. When I divide x by x, what do I get? Excellent! So this is the same as 1 over x plus 2. Did I show that the two functions are equivalent by simplifying y2? I did, right? Okay, so let's look at their tables. So, first step, turn your calculator on, right? That's an important first step. We want a new document that's a graph. In y1, I want a fraction that is 1 over x plus 2. And in y2, I want a fraction that is x over x squared plus 2x. And now I need to look at their tables. So Control T. So all I can see in the table right now is the x column and the F1, or in our case, y1 column, right? So for y1, this is 0.3 repeat. Oh, no, it's not. There. Negative 2 is undefined. Negative 1 is 1. 0 is 0.5. 1 is 0.3 repeating. And 2 is 0.25. Correct? So if I'm in the table right now, right? If I'm in the table right now and I use my right arrow, it'll take me to F2, or in our case, Y2. So would somebody read me the column for Y2? Undefined. 1. Undefined. 0.3 repeating. 0.25. Excellent. Wait, maybe not excellent. In what ways are the tables not equivalent? So at x equals 0, look what's happening at x equals 0. Aren't these supposed to be the same? And they are not. Sketch the graph of y sub 2. I'm going to go back and look at my graph. My graph looks like this. Does your y2 graph look like that? How many vertical asymptotes does this graph have? There's one vertical asymptote, right? Does this match the information in the table for y sub 2? For y sub 2, how many vertical asymptotes does it look like we should have? 2. Does it match the information in the table? No. So at this point, we're going to go, do it. Why are we doing that sound? Doesn't seem right. Something's interesting, something's wonky, right? But it's not time to explain it yet, so we're going to do another example. Right here. Find the vertical asymptote of this function by setting the denominator equal to 0. I wish they would have just said find the vertical asymptote, because then you would have to remember that to find the vertical asymptote, you set the denominator equal to 0. Okay, so we did that yesterday, so I'm just helping you remember, right? So 2x minus 6 equals 0. So add 6. So 2x equals 6. So x equals 3. Generate a table for this function. X squared minus 3x. Aw, dang. X squared minus 3x. 2x minus 6. Control T. So 0. Somebody tell me the table so I can write it down. 0. 1 is 0.5. 2 is 1. 3 is undefined. 4 is 2. Does the table support the location of the vertical asymptote? Yes, why? It's undefined, right? Now sketch the graph. Control T. What is strange about this graph? It's a line. What else is strange about this graph? There's no asymptote. Quick commercial break. Everybody ready for a commercial break? Look at my work. Look at my sentences. They're horrible. Fix them. So capital I. And then O period at the end. Capital T. We could even put an exclamation point right there, right? But sentences require what at the beginning? Capital letter, and what at the end? Some sort of punctuation. Okay, back to the show. What are we going to say after this? Because again, something's weird, right? This is not what we expected our graph to look like. Did any of you put this in and go, oh no, I must have put something in wrong? Well, that's what mine looks like, and I didn't put anything in wrong. So something's wonky. Okay? Usually values of x that make the denominator equal 0 will create what? Yep. A vertical asymptote. Can we take a real quick commercial break? Real fast? Guys, this word is asymptote. It's not asymptote. We're not in science talking about isotopes. Okay? There's two T's at the end. I agree that there's a P in there, but only one. So we say asymptote, like we're carrying it, a tote. Is that good? Okay, back to the show. Usually, values of x that make the denominator equal to 0 will create a vertical asymptote, unless that value makes the if that value also makes the numerator equal to 0, then it creates discontinuity, removable discontinuity. Now, you guys know I like to be honest and straight up with you about things in here, right? I had to be honest about this day. I'm 47 this year. Okay, I'll be 48 in March. And sometimes, because I work in a high school, I laugh at things that you guys laugh at, even though as a 47-year-old I should not laugh at them. Like, I think asymptote is funny. Okay? But today, after talking about asymptotes for 2 days, we have to talk about removable discontinuities, because the other word for removable discontinuity is a hole. And I laugh every time I teach this lesson, because we just spent 2 days on asymptotes and now we're talking about holes. Are you going to be okay with that? Okay. That's okay. We can be silly sometimes. That's fine. Okay. Are we past the giggling, though? So we don't need to giggle through the whole rest of the lesson when I talk about a hole. Okay? So when I say look for the hole, we're not all just going to start giggling? We're okay? Okay. We're given this problem right here for our third example. Okay? The directions are to factor the numerator and the denominator. But they did it for you because they want us to see something. If we factor the numerator, what's common is an x. When we factor it out, we get x times x minus 3. When we factor the denominator, remember that's a trinomial with a leading coefficient of 1. So we say what multiplies to be negative 3 and adds to be negative 2? What is it? Negative 3 and positive 1. Do you notice right here that there's the same factor in the numerator and in the denominator? When that's true, we take that factor, set it equal to 0, and solve that, but that gives us a hole. Notice that 3, where we think there should be an asymptote, it's only a hole, because 3 makes the numerator equal to 0 and the denominator equal to 0. That's not a vertical asymptote, that's a hole. But please also notice there's another factor in the denominator that right here, that's this x plus 1. Well, if we set that equal to 0, that is a vertical asymptote, because there's not a factor in the numerator that is x plus 1. Do you see the difference? The x minus 3 is in the denominator, but it's also in the numerator. That's a hole. X plus 1 is in the denominator and not in the numerator. That is a vertical asymptote. Think back to yesterday real quick. And remember, when the question was asked, how do you know that there's a vertical asymptote there? And you said, well, because the table says undefined. Do you remember what I said? I said that'll work for today, but it won't work for tomorrow. Do you see why it's not working now? Okay, good. So, let's fill in our definitions right here. If you plug in an x value and get a number over 0, the graph will have a vertical asymptote. But if you plug in a value and get 0 over 0, the graph will have a But like we talked about just a moment ago, the table is going to say undefined or error no matter what. Whether it's an asymptote or a removable discontinuity, it's going to say undefined, right? We should change that. Undefined. So for sure, to know for sure, we have to factor. Everybody understand? So I'm going to show you, well, maybe. I'm going to show you problem number 3. I'm going to do problem number 3 for you. I'll do way in so you can see it really well. Okay? I'm going to do problem number 3 as the example. You have the other 5 to do for homework. Yes? So, what do we need to do first? We need a factor, right? We need to factor both the numerator and the denominator. So if I look at the numerator, it's a binomial. There's no squared terms, but both terms are divisible by 2. Very good. So if I factor out a 2, what's left? X minus 5. The denominator is so it's a quadratic, but it's a trinomial, right? And the leading coefficient is 1. So we can say what multiplies to be the last term and adds to be the middle term. So what two numbers multiply to be negative 5 and add to be negative 4? Positive 1 and negative 5. So I can say x plus 1, x minus 5. So now we have to decide what to do first. Okay? First of all, I need to make sure you understand that this doesn't actually say Harvard, because that's actually not how you spell Harvard. What does this mean? It doesn't have anything to do with laughing. Okay? Horizontal asymptote, vertical asymptote. Yeah, we'll work on pronouncing that more later, but that's okay. You did pretty good. Okay? Removable discontinuity. Okay? We'll work on spelling even later. How about that? Okay? I did try to make it easy by making that the title. Okay? But then again, that's plural, and you usually need it to be singular. Anyways, back to the show. Problem number 3. Horizontal. How do we find horizontal asymptotes? Did we even have to do this at all to find a horizontal asymptote? And in fact, some people, when they do this homework, they go through and do the horizontal asymptotes first and get them out of the way. Because it's basically looking, right? Or remembering the rules. So what are we looking for when we're doing horizontal asymptotes? The degree. So what's the degree of the numerator? 1, because that's right here. What's the degree of the denominator? 2, that's right here. Compare them. The denominator is greater. So, are you positive? If you were not positive, what could you do? You could look back at your notes. Absolutely. Okay? That's like the whole reason I give you notes, is you have them to refer back to, right? Okay? But since the denominator is greater, we know that there's a horizontal asymptote at y equals 0. Now I have to decide about vertical asymptotes and removable discontinuities. What do you notice? There's an x minus 5 in the numerator and in the denominator. What is that going to give me? That's going to give me my whole. That's going to give me my removable discontinuity. To find it, I say x minus 5 equals 0. So x should equal 5. But before we write anything in the lines, I have to make sure that something is very clear to you. Okay? If I look right here, I have what? I have an asymptote. If I look right here, I have an asymptote. Right? What is this? It's a line. What is this? It's a line. What is that? It's a hole, so it's a point. Right? So an asymptote, we know there's nothing there, but we represent it with a line, right? An asymptote, we know there's nothing there, so we represent it with a line. A removable discontinuity is a hole. it's not a line, it is a, right? Nothing's there, but we represent it with a point, correct? So I can't just write x equals 5 for my removable discontinuity because that implies it's a line. I have to write it as a point. And is it going to look something like that? How do I go about finding the y value? Plug it in. Okay, so 2 times 5 is 10. 10 minus 10 is 0. Okay, 5 squared is 25. 25 minus 20 is 5. Minus 5 is 0. 0 over 0. Dun, dun, dun. 0 over 0 is not 0, guys. Nope. It's not anything. It's bad news. Like, yeah, calculators explode because of that. Okay? Like, looking back up here, though, isn't that a specific point? And if I took the x value of 3 and plugged it in here, right here, I'd get 0 over 0. That's because I know that's what makes it a removable discontinuity. There has to be a value for that point because it's not on 0, is it? So watch this. What if I go to my factored equation and ignore that? 2 over 5 plus 1. What's 5 plus 1? So what's 2 over 6? 1/3. That's how I get my y value. I take this and plug it into what's left, not including the factor that they have in common. Does that make sense? Now what's left to do? Removable discontinuity, and where does that come from? It comes from the other factor that the numerator does not have. How do I find the vertical asymptote? Set it to 0. X plus 1 equals 0. So x equals -1. Does that make sense? So, for most people, not you, ha 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 ha, but for most people, what's the hardest part of this problem? Remembering how to factor. Okay? We did it before break. I told you it was super important because we'd be doing it a lot in the future. Well, it's the future. We gotta start working on it today. Okay? Any questions on this? Real quick, walk me through how to find a horizontal asymptote. Look at the exponents, right? The degrees. How do you find a vertical asymptote? Set the denominator equal to 0, but not something that's also in the numerator. How do you find a removable discontinuity? Something that's in the numerator and the denominator, we set that equal to 0 to find the x value. We plug it into what's left to find the y value. Does that make sense? Any questions?